Before you guys finish your homework assignment, I wanted to walk you guys through all of number one, the first and the second page, dealing with pendulums. How do we think about what's going on with the speed of a pendulum, what's going on with energy and energy conservation, and how do we graph things like how velocity changes over time, or kinetic or gravitational potential energy changes over time. So the homework assignment I'm referring to is AP Physics 1, Unit 8, Worksheet 1, titled Simple Harmonic Oscillators. And I'll provide a link in the description video below, which brings you guys to this if you want to. So all of number one deals with the same situation, a pendulum swinging back and forth. So let's read it. An object of mass 1 kilogram is attached to a string of negligible mass, which is fixed to a pivot point as shown in the diagram above. The mass is pulled back to a height of 0.3 meters from its original resting position at position C, and released from rest at position A. Part A says, create an energy bar graph for the object Earth system for each position of the mass at positions A, B, C, D, and E. So position A is where it starts from rest. So if we look at the energy bar graph, it's not moving, so it has no kinetic energy. If we define our height of 0 as the height of the pendulum or the mass at position C, at position A, it's 0.3 meters above, so it's got some gravitational potential energy. There's no springs involved, and let's assume all of this is frictionless. And so there's no kinetic energy, but there is some gravitational potential energy. So let's just say there's 4 bars of gravitational potential energy. Once the pendulum gets to position B, it's now lower. It's probably looks like about a quarter of the height, or less than half of the original height, so there's going to be less than half the original gravitational potential energy. For the object Earth system, if there's no outside forces on it, there's no work done, so that means the total energy of the pendulum system has to stay conserved. Energy is conserved, and so as the gravitational energy decreases, the kinetic energy of the system has to increase. So at position B, it's going to have some kinetic energy because it's moving, and it's got less gravitational potential energy. By the time the pendulum gets down to position C, it's at a height of 0, so all of its gravitational potential energy is gone. It's all transferred to the kinetic energy account. At position D, it's now rising, so the gravitational energy will go up. The kinetic energy has to go down because after the pendulum passes position C, it starts to decrease its speed until position E, its velocity or speed has to go to 0. So at position E, when the velocity is 0, all of the energy be stored as gravitational potential energy. So part B asks, how much time would it take for the pendulum to start from position A, make one full cycle of oscillation, and return back to position A? Well, if the pendulum starts at position A, goes through all the way to position E and all the way back to position A. That's one complete cycle. The time for one complete cycle, remember, is defined as the period of a pendulum system. And we have an equation for that, which we've previously discussed. The period, or capital T, of a pendulum system is equal to 2 pi times the square root of the length of the pendulum divided by the gravitational field strength of the planet that this pendulum is swinging back and forth on. Remember that the only thing that affects the pendulum is the length. The mass doesn't matter. The initial angle that it's released from doesn't matter, assuming that that angle is small, or relatively small. So for this problem, we've got 2 pi times the square root of the 1 meter length. That's the length from the pivot point to the center of mass that's oscillating back and forth. And if we divide by the gravitational field strength of the Earth, about 9.8 newtons per kilogram, that gives us a period of approximately 2 seconds. So it takes 2 seconds for the pendulum to go from position A to E and all the way back to A. And if it takes 2 seconds to go from A for a full rotation, it's going to take 1 second to go from A to E. What about part C? When does a swinging object have its maximum velocity? And then calculate this maximum velocity. Well, this mass will have its maximum or biggest velocity at the position it has the most or maximum kinetic energy. If we look back at our answers for A, it had the most kinetic energy at position C, because all of the initial gravitational potential energy gets transferred to kinetic energy. So let's do an energy conservation problem. From A to C, it's going to go from initially only gravitational potential energy at position A, and all of that is going to be transferred to just kinetic energy at position C. So if we plug in our equations for both gravitational potential energy and kinetic energy, we get mgy, the height at position A, is equal to 1/2 mv squared, where v is the speed or the velocity of the object at position C. In this case, the masses end up canceling out, and if we solve for the velocity at C, we get that it's equal to the square root of 2 times the gravitational field strength, just used 9.8 newtons per kilogram, times the height at position A, or the vertical position at A, which is 0.3 meters. When we crunch the numbers, we get that the velocity at position C is equal to plus or minus the square root of 2.4 meters per second. This is its maximum velocity. Remember, when we take the square root of something, the answer is positive or negative. And in this case, that makes sense because as it goes from A to C, once it goes from A all the way down to C, at position C, it's moving to the right. So it would have a maximum velocity of positive 2.4 meters per second. Then the pendulum would slow down up to position E, stop, and then speed back up as it goes to position C. The next time it gets to position C here, it's going to be moving to the left, so it's going to have a big velocity, or a big speed, moving in the negative direction. So let's first talk about how we would show what's going on with the velocity as a function of time. So let's say that at time 0, the pendulum starts at position A. So we know at time 0, we have to have some dot at 0 seconds. The question is, well, how long does it take to go from A all the way back to A? Well, remember, that's what we figured out in a previous part. That was the period. It took about 2 seconds. And so by the time the graph gets to the 2-second mark, it has to be back at position A. If it took 2 full seconds to go all the way out and come back, that means it's going to take half that time to make it to position E. And so it's going to be at position E at 1 second. And similarly, if it goes from A to E in 1 second, it's going to take half that time to get to position C. And so it should be at position C at both a half of a second and 1.5 seconds. So we know at least what times it's going to be at those positions. And we should be able to think through what's true of the velocity at each of those positions. Well, at position A, remember, it's going to have 0 velocity. That's where it starts from rest. Once it gets to position C at a half of a second, remember, that's when it's traveling the fastest at its maximum velocity, and we calculated that to be 2.4 meters per second. So we'll put a dot there. When the pendulum reaches position E, it's gone back to a 0 velocity. It's come to rest again, and it's going to reverse directions. So it's going to swing back, speed up, and when it gets back to position C at 1.5 seconds, it'll be moving the fastest, but in the negative direction. And so we have to place the velocity at negative 2.4 meters per second. And once it gets back to position A, it will again reach 0 velocity. So we at least have a few points on this velocity versus time graph. Then the question is, what is the shape? Do we connect these with straight lines? Are they curved lines? How do they curve? Well, if you remember back to a previous video, we showed that things undergoing simple harmonic motion or oscillating back and forth, their velocity changes like the shape of a sine or a cosine curve. And so if we're going from 0 to a positive value to 0 again, down to negative and back to 0, the shape should look something like this. For the last part of question number 1, we're going to do the same thing, except think through what's going on with how kinetic energy changes over time and how gravitational potential energy changes over time. You guys should be able to identify at what time the kinetic energy will be maximum and minimum, and the gravitational potential energy will be both maximum and minimum. But in order to figure out exact values, we need to know what those maximum kinetic energy values and maximum gravitational energy values will be. So, kinetic energy will be maximum when it's moving the fastest at position C, and when it's at position A and E, it's going to have 0 kinetic energy because it's not moving. So what's the maximum kinetic energy value? Well, let's use our equation, 1/2 mv squared. So 1/2 times the mass of 1 kilogram times the maximum speed of 2.4 meters per second squared gives us a maximum kinetic energy that the system has stored of 2.9 joules. Well, what about gravitational potential energy? It's going to be maximum at both positions A and E when the pendulum, or the mass, is the highest above a position 0, and when it's at a height of 0, it has 0 gravitational potential energy. So the value for that maximum gravitational potential energy is equal to mgy at either the height at position A or C. So it's 1 kilogram times gravitational field strength of 9.8 newtons per kilogram times the height of 0.3 meters gives us the total gravitational potential energy of 2.9 joules. So what does the graph look like? I'm just going to show you and talk through it. So remember, the kinetic energy is going to change over time, and the shape of it's going to be like a sine or a cosine curve or similar to it, and the same thing with gravitational potential energy. So kinetic energy will be in red. At position A, it's at 0. It's max at position C, which we calculated to be about 2.9 joules. Then it's at minimum again once it reaches position E, maximum at position C, minimum at position A. Kinetic energy versus time graph or a gravitational potential energy versus time graph won't have negative values. So the minimum will always be 0 and the maximum will always be some positive value. For gravitational potential energy, it's that same shape and the same size. It's just kind of mirrored vertically. So at A, it has its maximum gravitational potential energy of 2.9 joules. Once it gets to C, it's at a height of 0, so the gravitational potential energy will be 0, and then it will change just like this. A question that you guys weren't asked, but we should be able to think through is what's true of the total kinetic energy of the system? Well, for the pendulum Earth system, the total energy will be equal to the sum of the gravitational potential energy and the kinetic energy at any point. It's easiest to see when you only have gravitational potential energy, let's say at position A, or only kinetic energy at position C. So the total energy of the system is 2.9 joules at position A, and it's 2.9 joules at position C. Well, what about in between? Well, if we add these things up, it turns out that assuming there's no work done on the system, in this case, we can, assuming friction is negligible, that means the total energy of the pendulum system the whole time is constant. We made the assumption that energy is conserved. So the total energy of the system stays constant at 2.9 joules. Now you guys should be ready to finish the rest of worksheet 1.